Hello everyone, I am going to talk about a chemical problem that sits inside almost every home. A group of chemicals called PFAS. People call them forever chemicals because they do not degrade in normal conditions. In this work, we show that calcium metal can break these chemicals on its own at room temperature without any additives. This study is published in the Journal of Physical Chemistry C. Here is the plan. First, I will discuss what PFAS substances are and its impact on society, environment, and human health. So, then the real challenge why they are so hard to destroy. After that, our main result, that is a calcium metal surface that pulls these PFAS molecules apart. And finally, I will conclude my talk with some future directions. Now, look at the two molecules on the left. The top one is a normal fatty acid where a carbon chain is attached to hydrogen atoms. The bottom one looks the same, but here the hydrogen atoms are being replaced with fluorine atoms. So that one small change makes all the difference. Now the major part of these substances, PFAS substances, are carbon-fluorine bonds, which provides them exceptional thermal and chemical stability. Moreover, due to low surface tension, they are both hydrophobic as well as oleophobic in nature. So now the tail repels both water and oil at the same time, and the head can be a carboxylate, a sulfonate, a phosphate, or any other functional group. That combination is why the molecules are so useful and why nothing in nature can break them. So, due to all these unique properties, they are being used in various industrial as well as household appliances, including non-stick cookware, firefighting foams, etc. You might have used one of these PFAS substances today. So, they are extremely well, which is exactly why we made so many of them and more than 12,000 different kinds. So, now look at the right side. These are the measurements from human tissue. PFAS turn up in lungs, in the liver, in the bone, even in the brain. Once they go in, they start accumulate and they stay there forever. So now the question arises, how do they reach us? From this flow chart, you can see that they comes from factories, sewage plants, landfills, and they move into water, soil, and groundwater, and finally into the food chain. So once they enter inside the living organism, they have been linked with different diseases including kidney problem, higher cholesterol, effect on immune system, and changes in the liver enzyme. Our bodies have no enzyme that can cut a carbon-fluorine bond, and so these molecules just keep building up inside the human body. So this is a study which suggests the presence of the PFAS substances in the drinking water resources across the United States of America. Here the blue regions are places where the PFAS were detected. The hotspots sit near industrial areas, airports, military firefighting or military fire training areas, and waste water treatment plants. So here you can see that the PFAS are detected almost everywhere. And back in 2016, the safety advisory was 70 parts per trillion. Notice the unit, parts per trillion. That is roughly one drop in a very large swimming pool. And even that limit was later tightened to 4 parts per trillion because these chemicals are far more toxic than we first believed. So, by considering the widespread presence of the PFAS substances around us and their harmful nature, it is essential to degrade them. So, here we have explored the reactive metal surface to degrade the PFAS substances. So, having understood the problem, we can now discuss the motivation behind the work. The motivation for this work comes from the calcium ion battery. We already know from the battery research that calcium metal destroys fluorine containing electrolytes. So that is bad news for batteries, but a very good news for us. Moreover, calcium is also cheap abundant, and much safer to handle than sodium or lithium. So, in this study, we have considered calcium surface with 8 different PFAS substances. We have considered both short chain and long chain PFAS, out of which 3 belongs to perfluorocarboxylic acid and other 3 belongs to perfluorosulfonic acids. When environmental protection agencies banned PFOA and PFOS, fluorochemical industry started using GenX and PFOS as a substitute PFAS to these chemicals. So later it was realized that they are also equally toxic in nature, so we have included these two PFAS in our study. This is the computational details. So we have performed ground state Born Oppenheimer molecular dynamics simulation using CONSUM DFT as implemented in CP2K. So these are the other computational details. So here you can see the PFOA on a calcium surface after 7 picoseconds of simulations. Here you see each green fluorine atom has left the fluorinated carbon chain and now sitting on the metal. So this is the same thing with 43 water molecules because the PFAS are water pollutants. So we have considered the water molecules. So now these graphs tells us why the defluorination occurs. So here you can see that around 10 to 12 electrons flow from the calcium surface to the PFAS molecule. You can see that the red line goes up and the pink line comes down. We suggest that most of the charges are coming from the calcium surface to the PFAS substances, and moreover most of the charges comes from the top layer of the calcium, that is the layer touching the molecule. Calcium is literally handing over its electron and the PFAS molecule falls apart. Importantly, this also works in water. The water takes some of the charge but the molecule still breaks. So now the heat maps makes the process very clear. Each row is one carbon fluorine bond. The dark blue means the bond is intact, yellow means the bond is broken. So watch the yellow spread from left to right. That is, the defluorination is happening in the real time. And for PFOA, everything is yellow after 3 picoseconds. And below is the evolution of the carbon-carbon bonds. Here you can see that in the beginning, the bond length of this carbon-carbon bonds was around 1.5 angstrom, which belongs to a carbon-carbon single bond. As time proceeds, this distance shrinks to 1.3 angstrom, which suggests carbon-carbon double bonds and triple bonds are forming. So as the fluorine departs from the skeleton or from the molecule, the skeleton left behind turns into a simple unsaturated hydrocarbon chain. So now look at this movie frame by frame. Here you can see that at 0 femtosecond the molecule is floating about 4.5 angstrom above the surface. Now it turns itself so the acid head and the nearby fluorine face the metal, and at 650 femtosecond the first carbon fluorine bond breaks. Then a chain reaction occurs where fluorine after fluorine leaves one carbon at a time. You can observe two nice details here. The first one is the fluorine leaves in a trans pattern on opposite sides because that is energetically more favorable. And the second is at one point the departing fluorine grabs the acid hydrogen and leaves as hydrogen fluoride. So by roughly at 3 picoseconds the molecule is completely defluorinated. We saw the same story for perfluorooctane sulfonic acid. The only difference there is the sulfonate head dissociates first, then the defluorination occurs. So now this is the study with water molecules surrounding the PFAS molecule. So here you can see that most of the carbon fluorine bonds break within 10 to 11 picoseconds. The difference is that here water molecule supplies hydrogen atoms, so the bare carbon picks up hydrogen instead of staying bare. You end up with an alkene type of product that is an ordinary hydrocarbon, and that is actually useful. So bacteria cannot eat PFAS, but bacteria are very good at eating hydrocarbons. So even a partially finished job hands the rest over to the biology. So this is the robustness of our study. Here you can see that the calcium surface can degrade the long chain, short chain, acid, sulfonate, amides, genex. All of them break down on calcium within 7 picoseconds. And this is important because most of the existing methods work on one or two well-known PFAS substances, but they fail for other set of PFAS substances. But here, calcium doesn't care about the chain length or the head group. So irrespective of the chain length or head group, it completely defluorinates all the selected PFAS substances. And one more question we ask here is, why do only carbon fluorine bonds break, not the carbon-carbon bonds? The answer lies in the thermodynamics. The calcium fluoride is more stable and its heat of formation is about minus 1200 kilojoule per mole, whereas the heat of formation of calcium carbide is minus 60 kilojoule per mole. So that is why calcium wants fluorine and it doesn't want the carbon, and that makes the process clean and very selective. So there are three major conclusions. The first one is the calcium metal degrade PFAS at room temperature with no additives and no heating. So the contact itself is enough to degrade the PFAS molecules. The second is this happens because calcium is strong electron donor and calcium fluoride is extremely stable. So these two factors work in a synergetic manner. So the final one is the products obtained here are harmless. The fluorine ends up as calcium fluoride. So the same mineral as fluoride, which industry already uses to make hydrofluoric acid. The carbon ends up as simple hydrocarbons. So nothing toxic is left behind. So moreover, we also saw the fluorine sink down into the deeper calcium layers, which suggests the surface can keep working on new molecules and can be refreshed if it ever slows down. So thank you for your kind attention. Thank you all.